Good evening all. We're going to do a little bit of something different, a little bit of hardware today. And today I'm introducing you to this little board here called the Highfive from SiFive or SiFive, if you want to, the Freedom Everywhere board. Now what makes this thing so unique and what I'm trying to, well, so important, I'm trying to show it off, is because of this little chip right here. That one. Go that way. It has the SiFive on it. This is a RISC-V chip. This is the first commercially available board with it. This is a Arduino compatible board, so it's kind of like this here. This one, well, upside down. This one here, I got it in the kit. See, this one's a Freetronics Arduino Uno, which is pretty cool. Now, first and foremost, why is this one so good? Well, that RISC-V processor. This is an actual processor compared with the Atmel thing here, which is rudimentary at most, so to speak. It is a microprocessor, but it's very rudimentary at best. Now, what is RISC-V? RISC-V is the latest attempt, really, at a RISC CPU. Kind of like the ones you got in, like these. This is, except the one on your phone is ARM. This is something completely new. However, unlike ARM x86, which is like from Intel, AMD, that sort of thing, this is completely open, completely free. You can do whatever you want with it. It's a free standard. So what this means is RISC-V is not an actual CPU per se. Like this chip here, this one here, is actually a Freedom E300. It's an actual core. You can actually go to GitHub and look at all the files. This whole board is completely free and open source hardware. You can get the actual schematics for it. You can get the Gerber files. You can get the bill of materials. So you could technically build this yourself. And this board here only costs about $60. So right now I'm just running this LED flashing thingy, cycling thingy on it at this point. So let's go to the GIMP and I'll explain what RISC-V actually is, and we'll see how we go from there. Sorry, this is completely unplanned. I do have some examples I got floating around, and I did try to prepare, but the actual main particulars of this recording are, well, different. So let's go have a looky over here at the GIMP. And actually, while I'm here, I might put a new thingy up here. Hold on. Add existing key, so you can see the board. There we go. So, what is RISC-V? Well, RISC-V, you got to know what CPU basically is at this point. So I'm going to need my pencil. Where's my pencil? You need me pencil. Okay. So, Jesus Christ, that's huge. Don't need that big. That'll do. So, a CPU basically is so you got your CPU, right? Okay, a CPU is basically made up of your arithmetic, your logic, and then all this space is your transistors, and a little bit down here is your accumulator. So that's all well and good, but that's in the bare silicon itself. So, okay, I'll try to explain this a bit better. Yeah, alright. So like Intel has instruction sets. Every CPU has one. They all have their own instruction sets, like when you're doing assembly or stuff like that. So like Intel's MOV to some address, 5 to another address, say 6. Oh, C6. That's valid. And stuff like that. what RISC is means reduced instruction set. Essentially means the whole thing, the whole core of the CPU. This thing here, and basically these two, your logic and your arithmetic here, is completely open, completely free, and completely done. And it is being worked on by many people. So this little chip is essentially the CPU equivalent of open source software. And there is so much going on. So what this means is, so anyone can build their own CPU based off this, but there is standards compliance to be a RISC-V. You have to have certain standards, and what that means is your instruction set space is of limited size, right? It's about that big. The RISC Foundation take about that much. That's your standard. So that's reserved for your standard stuff. Okay? So you got your base instructions. So you got your B in there. Then you got some extensions like your math. So multiply, divide ones, because they're not included by default. Some embedded stuff, and a few other things. So, but over here, this is yours. So you can add on your own extensions. Say memory buffer. So say a buffer of sort, memory buffering, or caching, or something like that. So you have like an instruction caching in the CPU itself. Let's say slimlining stuff. So you can slimline your instructions so it rearranges your instructions as they come in to be better optimizations. I'm not exactly sure. But then you can have, say, a lot of the free software purists and me are gonna hate me for this, but you could put some some DRM in there. Why? Doesn't matter. You can do that. The RISC-V Foundation is not adverse to commercial use of this, of course, for commercial means. Anyone can put their own closed extensions to this. What is open and what is actually free is this core instruction sets. That is. So companies can build their own here, and if they want, they can contribute them back to the foundation and say, hey, we made this, and this might be important to other people. Or they can say, oh, we just want to keep them. So like Samsung, for instance, can have their own instruction sets here for the phones or stuff like that. So what this one is an so it's an E310, and yes, it has its own instruction sets. It has its own extensions built in and has its own little pipelines built in. So it has its own extensions here, but while still using the standard extensions. You can go off, you see there's a big gap here. You can go in here if you wish with your extensions. You can make your extensions this big if you want. However, that does not mean your system, your core, are going to be compatible with the new version up here. Like, say you got all these extensions. Now there's a new extension you want to use, but you can't use it because you're already using it. So you got no room to put it. So basically what this means, what the RISC-V allows companies and individuals to do is to basically design their own custom CPU without going through the whole process of rolling their own CPU. So designing their own thing through Chisel or something like that. They can just use this and they bolt on some extensions, get it extended out, and get it built, and here you go. Nice little chips. That big one here is actually solely for the USB and JTAG stuff. So why is this so important, and why am I showing you a little board with the RISC-V on it? This was designed by the SiFive people. So yeah, see, they're branding on the back here. So SiFive. So they were able to roll this out in great quantity on their own. They have complete control over it. They can say what's in there, what it does, and how it does it. And more importantly, because it is designed and optimized for reduced instruction sets and whatnot, this little baby runs quite fast. So we have the little Arduino here, Arduino Uno, this Atmel chip, which is right there, which is actually quite tiny. It's not the smallest IC I've seen. That still holds to a RISC-V chip, which was developed not too long ago. This chip, this whole board, only runs at 16 megahertz, for instance. Since this is a proper CPU and a proper instruction set and a reduced instruction set, this little baby runs at 320 plus megahertz, there or thereabouts. So this thing is a lot faster than that, and I'll demonstrate that in a few minutes. So it's kind of hard to explain why I'm getting so excited about this. Because what this means is, since the core is free and open, anyone can build their own CPU and whatnot, this means that companies are no longer have to pay exorbitant fees to, say, Intel for the x86 architecture. There's no patents or IP issues or whatnot. On a RISC-V processor core, so this core, the software I've written for this will work on another board that has a completely different CPU, but it still has an i5 RISC-V core. So that means we don't need Java virtual machines or something like that. You don't need a translation layer between the CPU and the software, because the software compiled for a RISC-V will always work on a RISC-V processor. Like I said, these extensions here, with these extensions, it just means that they've got some optimizations in different ones, so they run differently, they have different purposes, stuff like that, like industrial purposes, full-blown purposes and whatnot. Is this ready for the prime time? I don't know. The foundation says no, and some other people are saying no, but I'm saying have a go. I see no harm in it. But get back onto the point, what I was saying is, since this is free and open and CPUs can be made, Samsung can roll their own CPUs for their phones, for instance. And so they don't have to keep up with Android updates or whatever. The apps will work on it regardless, whether it's a Samsung S6 or 9 or whatever. If they do have the same core CPU, even though some are faster, some are not. It's like I can run the programs I make on my Intel machine that I have here, my i7. If I was to grab a 486, for instance, it will still run on a 486. Pretty piss poorly, but still run. Same if I code something on my i7, I can transfer that program across onto a Xeon, and it'll still work. Same thing. So this offers incredible flexibility. I'm going to go full screen for a second because I'm just rambling on. So this CPU and this board, by extension, offers huge amounts of flexibility. So you can put whatever you want in this thing, and it'll work. Now, granted, this is not a Raspberry Pi compatible board. This is not the same. You cannot boot an OS from this one. You probably could. Alan Cox, if you're watching, you're the one who's stupid enough to put a Linux on a TRS-80. Maybe you could put Linux on this. And on that note, all the software, the entire tool chain to build your own CPU, to compile for them, to do everything is freely available, and they're all there. The entire tool chain has been developed. You can use virtual machines, you can use all that stuff. It's in GCC modules already, the Linux kernel already. Fedora already supports it. There's Debian already supports it. It's there. The software is there. We just need We just need Microsoft to support it. Yeah, and that's not going to happen anytime soon. So, let's have some fun with this, shall we? Enough yammering on. Let's get some fun. Okay. So where is my desktop? There we go. Okay. So first things first. Like I said, we've got the blinky light. So when we're coding for this, we can use simple C, like this little hello program, hello world, which will work. So where's me terminal? Is that me terminal? Is it that one? No, not that one. This one. Aha, that one. Okay. No, I don't want it that high. I'll hide myself for a second. There we go. So what we do to compile for the C, like this is an example one. So I'm already, so we'll make it, we compile it. So program we want is simple hello. That's all I need to do. We'll compile it. And there we go. Now I can upload it to the CPU, but I just need to check one thing. Yep, we're still there. Still got our terminal open. So upload. Yeah. Oh. It's there and play. Hello world. And if I reset, just hold on. This board has a cool reset button, which is right there. It's the pinky button, and next one is awake. So if I press that, we should get a new one here. Did we? No, we didn't. We're getting something. Let's try that again. Upload. There we go. Core frequency is at 275 blah 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 hertz. Hello world, and it's exited with 0. It's reached its end. No problem. So let's try something. What can we do? Let's do some calculations, shall we? So we go A equals to the power of log. Hang on, that's not going to work. I don't have all the math stuff. Standard IO is not going to work. Ah, crap. So we're going to say 9. So A equals 9. I'm typing on an upright keyboard right now because it's right here in front of me. Times that again by Now divide it all. So hang on, I'm going to go. Is that divided by? So that divided by 8989. Times it by. That'll do. And we go puts A. I think I needed to declare my variables first. So string, oh no, double A equals 0.0. There we go. Now that should compile. And I have been meaning to do some videos on C compiling, like I want to go through the Blender source code for instance and make some changes in that. But anyway, let's see how we go with this, shall we? I'm going to bring this down now so you can see some lights blinky. Okay. So let's compile it. Okay. Now that's been compiled down into bytecode that I can then upload onto this. So upload. And what did we get? Hello world and We did something. Oh, we did something. Let's try that again, shall we? Why did that not work? Let's have a look over here for a tick. Oh, it has to be a char thingy. I see. Huh. Well, this is a much more complicated program, so I'm going to bring you up a little bit so I can show you more of it. This is the LED fade one that we saw earlier, which is why we have the SiFive logo there. So if I was to compile LED fade, for instance, it would do that. But puts. That's weird. How do I output a double then? Double the string. It's been a while since I've done me C. Well. No, there's no two string, I don't think. Well, I don't know. No. Well, anyway. Oops, did I even save it though? Sorry. Not sure if I even saved it. Just S. Now let's try this again. Actually, I'm not sure if I actually saved it. So make it. Aha! There we go. So something didn't work. Expecting constant char dot, but it's not. Hold on, I'm going to do a quick little Google. Double to char. I'll do. Okay. It says S print F, so we could do that. Let's try that, shall we? Let's try something, shall we? So what is it? It is. I'm sure someone's chucking the shit at me right now, so let's go. I'm not sure if this will work, but we'll go S print. Hey, come back here. Let's print F. Oh, god damn it. Keyboard fell. Sorry. Doing all this for not much, are we? Okay, so actually I will use my keyboard down. So sorry, it is a grubby keyboard. It is quite a grubby keyboard, and I'll move you over there for a tick. Okay, so we need a character array of, say, char. Is it? It is char. array. Just 200 of them. Nah, not do. 200. Let's printf. Oops, didn't want to do that. That one. Array. Good. So I hope this works. 2.13 F. If this doesn't work, then I'm terribly sorry. And I'm terribly sorry to everyone who is watching this, because my C coding has been long since gone. So let's compile. Error. Oh, what? Oh, whoops. That might help. One thing. That might help. Okay. Save. Make. Okay, now we're getting somewhere. Where's my board? Here's my board back. So let's put the keyboard back up a little bit. So, let's see what we get. Upload. What did we get? Same thing! Well, that didn't work. Oh, well, anyway. Let's do this LED one. So let's do the LED one. We know that one works. So let's go make. Sorry about that. Fade. And while that's doing that, why I love this machine is exactly this. I do not need to boot it. I do not need to wait for it to boot, unlike the Raspberry Pi, because that is just basically a computer, just a credit card size machine. So upload LED fade. But then again on this, you could technically do Hangman or something with the terminal. Okay, so it's up. And there we go. Are the LEDs changing? Can you tell me? They're changing? I think they are. And we type yes. Pass. Good on ya. So yes, we can do C coding with this. Same with this. We can do C coding with Arduino. Pretty much any device you can compile code for using C language. But this is a bit slower. But to demonstrate what to do, I didn't really want to set up a C compiling for this thing, because that is just annoying. So what I'm going to do is, we already used the Arduino. Since this is Arduino compatible, that's the wrong one I wanted to show. Yes, this one. Let's do this one. Yep. This little program here, all it does is just loop through some values and light up some LEDs, which I have here. I just need to plug them back in. So, first of all, I'm going to unplug the Highfive. I'm going to go use the Arduino Uno. So, we've got our base comparisons to do. Actually, no, I'm not going to plug you in just yet. Let's move you. Alright, so let's plug you in. So what I remember, it is wrong way around. So you go into 2. In case you're wondering, these two here are, these two pins are the same. All the pins are pretty much identical across them. So you can tell the pin outs are pretty much identical. Except I don't think this one has any analog. I don't think the SiFive, this Highfive, has any analog inputs. I'm not sure. I have to go look for it, because I was looking earlier and it's slightly different than this. But anyway, so and what I was saying is, these two here are actually transmit and receive signals. So you can use your Bluetooth or something like that with that one. So I'm skipping these first two because they aren't used. and you go there. No, I've got them back to front. No, I do have them right way around. Yeah, that way. That one goes like that. That one goes like that. And there's a little chip in here, called a shift register. All it does, all this little chip in here does, is take in some data and spouts it out the other side. So it takes in some data from this side and spits it out the other way as a byte. So a 1, it gets current. If it's a 0, it gets no current. So essentially it brings out a binary. So we got this here. Let's bring some power to it, which is... I've got this around the wrong way. So at this point, that's one thing I like about this thing. Look, big writing, big good writing on the silk mask. This one, not so much. So I'm going to go bigger screen. Where are we? Yes, you. See, look, compared to writing on these two, you can barely see this one in here. The tiny as, but this one's got nice big writing where I can see it properly. But this one has some ground pad. The Arduino has some grounding pads and some test pads here I could use, but with the multimeter. But at this point, no, it's just this. Anyway, let's get back to what I was doing. So let's plug you in. So yeah, so it's these two here, transmit and receive. So anyway, let's put you in there. You go in that one. And you go on that one. So now I am around the right way. So power, 5 volts. And that's another thing about this board I'm not overly fond of. Is the numbers don't quite line up with the holes. And some ground is there. It is that one. That is the ground. There. See? We're all hooked up. So where's the USB cable? There it is. I don't know what I've actually got, what program I got running on this one. I think it's something else. I think it's the other one I'm going to demonstrate. Oh, we've got some power on the LEDs. Oh, they're bright. They're very bright. So I'm going to have to, oh, why not? Where's my desktop? There we go. So I'm going to select my Arduino Uno, and the programmer is the Arduino ISP. So all we do, yeah, we can verify it. So it compiles the sketch down into bytecode. We can use C code in here if we wish, but don't have to. And we can upload it. Oh, wrong port. Port, that one. This Arduino uses a different port compared to other things. And oh, there we go. So let's bring it down to full screen again. There we go. Oh, that is looking horrendous on there. This one. So let's bring the exposure down a little bit, shall we? So you can see that a bit better. So you can see there's actually 8 LEDs in there. And it's just writing out a binary number. Yeah. Brightness, let's turn the brightness way down so you can see it. Now I'll bring it back up. So that's what that does. But what I'm going to do is I'm going to get, go back to up here, sorry. You can't really see them properly because the camera is over bright and whatnot. I don't know exactly how to do this. So let's do this. What's that do? I don't know overly a lot, but it does something. Well, anyway. So we got that. So what I'm going to go do is go back to our code here. And I'm going to comment out this delay here. So there's no delay whatsoever. Control S, thank you. And we upload this. Now watch. You can't really tell, can you? But there's one there. Oh, it's not working on this camera because you can't see it because the shutter speed. Okay. Well, what's happening is this one's actually flashing a lot. Like really, really fast. You can actually see it flashing. Hang on. Can I change? That's 30 frames. Can I change this up to 60 frames? Does it still show it? No, it doesn't. I'll go back to 30 frames then. Well, I wish I could show you, but this is actually blinking because it's taking so long to go through them. It's actually, these two are actually blinking here, but you can't see it. Well, there goes one of my demos. I was kind of hoping for. It ain't working. But anyway, just to prove how compatible this thing is, so let's unplug you. So let's plug in the SiFive, the Highfive one. Let's plug you in. So we got you, you, I think, and you to there. So let's get some power to 5 volt, which is right there, and the ground is over here with that. So I've got to plug you in. Yep. There we go. And change my board. Yeah, I know they're on because there's power going through it. And change you to the SiFive one. And no. So upload it. It takes a bit longer to build, but there we go. And you can see, yep, they're flashing because it's running at 16 megahertz, right? So you can see that. That's the actual, now it's actually showing it. It's actually running a little bit slower than the Duo. So hold on, I'll bring that back up onto the full screen. Bloop. See? So you can see it is actually taking its time and blinking. Now watch what happens when I go back to the desktop, to my desktop. So let's change up here. Let's change the CPU clock frequency from 16 megahertz XTOL to 56 megahertz PPL, or we go this one, the full 320 megahertz. And I know this is not the most efficient circuitry, and there's no resistors in there. And so now look, it is just on. There is no blinking, no flickering, nothing. It is running so quick that there's no discernible difference. It's just running through those numbers so goddamn quick. Yeah, and to show you that it is actually working, let's comment out. Let's bring that back in, put in a little bit of delay just to slow it down, and let's upload that. And see, so it is actually doing its thing. It was just running so fast. That's what happens. So that's the kind of why you would want to use this board, because of that speed, that responsiveness, that ability to read in and push out data at a lot faster than this thing, a way lot faster. So that means if you're doing robotics, for instance, you need trying to calculate all your inverse kinematics. Like, so for those who don't know, inverse kinematics is if I push on my finger here, sorry, let's move this forward. If I push on my finger here, my finger bends, right? What inverse kinematics does, it calculates where these bones should be, so I do this. And that is used a lot in robotics on arms and stuff like that. So this thing could do it, but it'll be a lot slower. It wouldn't be able to react to changes or difference in pressures and whatnot. This, however, This could drive that so goddamn quick and do all those calculations with pristine precision, because this is a full-blown 32-bit processor. This one, I think, is... I don't know, I think this one's only 16-bit. I'm not sure. But this is a full-blown processor. And yes, there is variation. There is a RISC-V 64-bit. And there's a RISC-V 128-bit that actually works and runs. So yes, there is that. But this thing... So that's what the cool thing about this speed when it's in this Arduino form factor. No, and I'm sure there's people wondering, is there a Raspberry Pi version of it? No. Quite frankly, I don't care. I think the Raspberry Pi is a bit too easy. And I hate waiting for it to bloody boot up. Then I have to interface into it to actually code it. Whereas this one, I don't need to plug in a monitor. I don't need to SSH into it. Just plug a USB into it, upload a program. Well, we're done. These sort of things is what you see in like car factories and whatnot. When you've got the robotic arms there, if you open these up, you'll see something like this. Let's get on to our next demonstration, shall we? I've got another cool circuit that works really well. So let's unplug this. Alright. Unplug my wires. Links to the RISC-V site and where you can get these boards. This board only cost me $60. There is a full-blown quad-core 1.3 gigahertz board that is Linux capable and everything like that, but that costs roughly $1,000. So I got this other little thing that I made earlier, that I prepared earlier. It is this. This is an RGB LED, and I have another program set up. So I'll zoom in. I'll go full screen so you can see the scene, so you can see what's happening. This is the circuitry here. It is just a simple RGB LED and some wires. That's all. And yes, I know there's no resistors or anything like that to save the LEDs and whatnot, and that's probably why this other one was a bit of an issue with the camera, because if it had resistors in there, it would have made them a lot dimmer. Quite frankly, I hate dim LEDs. They're too dull. And I know it prolongs their life and all that. No need to tell me. And by also, full disclosure, I should have said this earlier, but full disclosure, I am no expert. Alright, I am no complete expert. I'm just venting my opinions and my experiences with this. So let's work this up. Let's plug the Arduino, like last time, let's plug the Arduino in first. Now, this is a full-blown RGB LED. So, red is, well, red. And it goes into a... Nope, wrong way. Sorry. That was the wrong way around. Here's my Coke. There's my Coke. Ah, that's better. And so I need this one to be in 9. I think that's 9. Yep, that's 9. That is ground, this black one. So it can go, or the common diode, or whatever it is. No, that's ground right there. Green goes next to red. And down here. I forgot how much this actual kit I got this in actually cost me. I'm not sure. I think it was close to like $80 or something like that. From Radio Shack Australia. Yeah, there we go. I think that's plugged in. So let's go to desktop. Now I'm not just going to go some funky colors or whatnot. There is actual method in my madness at this point. Now where'd that cord go? There it is. Okay. So we're back here. Let's get our other program up and running, which is, I think is this one, which is this cool one. So I'm going to bring this down just a little bit. Now, some people, especially those in the computer graphics industry, might recognize this. If you don't, well, I'm sorry. Yeah. Anyway. Let's plug this in, shall we? Plug in the Arduino. It still has its old program on it, so it's not going to do anything. because it was connected to them there, not this here. Now I did earlier had a light sensor that I was going to use, but I couldn't figure out how to do n-log input on this one. So sorry. I'm going to bring my brightness back up again. Exposure. Bring that back up. There we go. Got an all dark. There we go. Focus. Not focus. Alright. So this code here is actually calculates what's called a black body. Sorry if it sounds racist and whatnot, but that's exactly what it is. Basically defining color, temperature to a color, basically a color to an RGB in this case. So it does. So if you look down, there's a lot of complicated stuff. There's some hard-coded values. I don't know where they came from. I just got this off the internet. It's not at all optimized, but that was on purpose because I wanted something to be really heavy on it, like really complicated and stuff like that. So what's it doing at this point? It basically does a random between 0 and 4,000. I'm not sure why it limits to that, but they said, no, do that. So it does all its calculations red, green, and blue, and then outputs them to the legs on the RGB LED. So let's get to it. So I'm going to change the board back to the Arduino Uno and the boot, that one, and port U. So let's verify just to make sure. Coding 101, never make assumptions. Also, I just saw this down here, which means that there's not a lot of stuff here. So it's got 2 meg of variable space, but the actual program storage space is only 32K on this thing. This board, this one here, has 8 meg program space, and all of that is on the chip itself. This thing has 8 meg on it. This little chip has 8 meg of memory on it. That's cool. But anyway, let's see what this thing does. So we do this. Program, upload it. And it's done its thing, and whoop, there we go. See, changing color, doing some random funky stuff. So I'm going to bring the exposure back down again. Ooh, all the way down. No, let's bring it back up just a smidgen so we can see it. So you can see it's doing all this random stuff because I think I put in a delay down there, but no, I didn't. I did not put in a delay. So you can see there's a certain speed to its changing. So let's plug this in. It is just going through black bodies, so it's like goes from red to blue, blah 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 blah. Basically, if when you've done a white balance or color temperature on your camera or something like that, that's what this is. So let's do this. Unplug you. Bring the exposure back up for a little bit. Might put it in automatic. How about that? Let's see what we get. So, this way. So, red. Goes into 9. 9. If you would like me to go through this coding for the Arduino, doing this Arduino code in a video of some sort, please let me know. I would love to do one. But then again, once again, I say again, I am no expert. I am no electrical engineer of any kind. This is very rudimentary, very basic, and I know I am breaking things at this point. I just don't have any resistors, and I couldn't be asked to go looking for them. So let's plug this one in and see what we get. So it's not going to do anything. We're just going to get a bright bluish, greenish LED. It's doing something. So let's change our board up here. So we go board. Highfive. The programmer is SiFive. And let's upload. It's just got to, since the build options change, it just has to do its thing. Altered, and yep, there we go. It's doing this thing, but it seems to be doing it a lot faster. It's a lot more skittish. Yeah, but I think we can do a better program, can't we? What do you reckon? So let's turn the exposure down so you can see it a bit better. Oh, that's right, it's in bloody automatic mode, manual mode. Bring it way down. Oh, that looks weird. Ooh, alright. So, let's bring it back up a bit. Okay, bring it down. Leave it like that. So yeah, I think we can improve this code a bit better. So instead of random stuff like this, like Kelvin here, let's do a for loop. Let's just loop through. So I'm going to bring down my keyboard again. Sorry if it's a bit grubby, but it is. So for int, I'm going to make it a double actually. Double. No, I'm going to make it a long. So in other words, it's a very long decimal point value. So Kelvin, while Kelvin, so while Kelvin, it's also while Kelvin is less than 4,000, and Kelvin equals Kelvin plus. No, actually, no. I'll just let it increment by 1. Just go like that. So do that. Down the bottom here. And if you'd like me to do some coding on C, because this is very close to C coding, so it's not far off. If you'd like me to do a video on that, that'd be awesome as well. So I've got you here like that. So it's just gonna loop from 0. So I've got to make this 0. It's gonna go from 7 to when it's less than or equal to 4,000. So it's going to keep looping over and over and over until it's less than that. At the end of each loop, just increment Kelvin by 1. That's what the plus plus means. So basically, the plus plus is shorthand for equals Kelvin plus 1. So basically, it's equals to itself plus 1. You can do anything you want in here. You can do itself multiplied by 1, and there is short code for that sort of thing as well. Or multiplied by a double thing. Multiply itself by something. Or divide itself. Or whatever you want it to do. But anyway, we've got all this stuff here. So, I'm going to actually bring this screen back up. Let's see if we can see anything coming out of this. Probably not. Hang on. Oh. To unplug you just so it stops, because I changed the actual screen value. So it is not that, it is up here. What did I set it to? That. So yeah, boop, boop. Well, there we go. It's actually doing something. So that's how quick it is going. So we can actually add some more stuff in here. Let's add, before it goes out, let's add some debug code, shall we? So we'll go, so red equals plus red. So let's copy that. C V. So red green equals that blue. So red green blue. And I'm gonna get this started thing up the top here. So I've got crack I'll put you there. So that's better. There we go. And oh, I didn't want to do that. I'm going to go here. Thank you. Okay. So let's see what we get, shall we? Upload. Oh, hang on. Whoa, look at that. But now it's red. It should be starting to go back up. Well, it should be. Oh, there we go. Now it's starting to go. Look at that. It is changing. I assure you, it is changing colour. Is there a backlight on? What's this? Let's try. So it is doing something, whatever it's doing. I'm just trying to fiddle with the camera controls here. I don't know what this is doing. It's just going nuts, but it is actually doing something. But yes, this is actually changing color as it goes. So let's plug in the other one. It's sort of a whitish greenish color, isn't it? At this point, a whitish bluish color. Well, it is actually doing something. Okay, I know you can't see it, but it is. Can I change it? Put it up here. Okay. What I will do is we're going to get rid of these because these are stupid now. They don't work. Oh, it's gone back down to red. See? Gone to red. We wait a little bit. It's got to go past 66, I believe. Then it's doing its... Oh, there we go. Now it starts to go to yellow. And now on screen, on your screen, it's white. It's yellow. But on my screen, it's a very dull yellow to my eyes. Yeah. Yeah, it's just taking its time doing all these calculations and whatnot. So hang on a minute. Hang on. I just got an idea. I just had a thought. What am I running this as? Oh no, 320 megahertz. Okay. So, okay. Let's upload and let's try again without all this nonsense going on. It started. There we go, that's better. It was all that printing that was making it go nuts. You can see, yeah, it is changing colour. There we go. That's how quickly it's changing colour. So let's plug in this one here. Let's see how long it takes, shall we? Yeah. How long have we gone on? Oh, fucking hour. Jesus. I better wrap this up. Alright. So, what we got here? We got this one. Okay, ground. Oh, wrong one. That's green. I need to put that one goes to there. Red goes in 9. Red goes there. Then blue goes here. Where did that thing go? Where'd that cord go? There you go. Right in my hand. No, I've got my hand Headphones, cord, and something. Oh, there we go. So let's grab you into here. Ah, that's still doing its random thing. So let's put these boards back to what it was meant to be. The Arduino Uno. You go to Arduino ISP. Yep, that one. Upload. See how long that takes? That takes a lot longer for it to change compared with this one does. This one was doing a lot faster than that. So actually, hold on here. Some cords. No, I'm not going to do that. I'll probably overload the LED. I was going to hook them both up at the same time. So if I unplug, oh no, I won't. Actually, while I'm closing off, because I've been going on for ages. So I highly recommend getting this. There's even, I just remembered, there's even a board you can get where you can actually flash your own CPU core onto it. It has a FPGA in it, specifically designed for testing of your own CPUs and whatnot. So you could theoretically design your own CPU, design your own RISC-V core, and have it run on actual hardware within a couple seconds. A couple things, and you can prototype it till the cows come home. Yeah, that's a lot faster. Anyway, with this little blinky LED going, hopefully you enjoyed this video. Yes, it is a very long one and a very rambling one. I just wanted to show the RISC-V here, this fantastic board. And I will put a link to pretty much everything that I've said. If I find a link to the board I was just mentioning with the FPGA on it, I'll see if I can find it, because I want to buy one, because I want to see if I can roll my own CPU and program my own CPU. That would be awesome. But anyway, I truly hope this RISC-V stuff takes off. And before I forget, NVIDIA is going to be using RISC-V CPUs, RISC-V microcontrollers in their upcoming cards, and so is Western Digital. Western Digital are going to have RISC-V chips in them as well. And there is news of RISC-V laptops being made, and that's going to be amazing. But I would like people who are watching this to go out and have a look. Get a kit like this, like I did with an Arduino. Not that bad. Where is it? Comes with a good manual. And I just got all my little crap and shit in there. I came with all these wires and a couple trannies and some resistors and whatnot. And, yeah. And a pretty cool book as well. So, see, book. That's a Freetronics kit. But anyway, check your local electronics store if you got them. They're fantastic. Don't be afraid to give it a go. If you can't do it, you can't do it. No harm, no foul. At this level, you can't do anything to yourself. You can't electrocute yourself. The worst you could do is probably pop a chip or something like that. Anyway, once again, thank you so much for watching. I'm sorry this is different than what my usual videos are. But anyway, I hope you enjoyed them. I hope you have fun with this, and hopefully you go out and actually buy one of these boards. They're only $60. Not that much. And I'll see you all in the next one. Bye bye.